Grouping and distributing. There are 5 different balls, as we can see, and 2 boxes. 5 different balls and 2 boxes. In how many ways we can put the balls into the boxes? So for the first ball, it is having capacity 2. There are 5 balls. We have 5 choose 2 option, because we need to choose 2 balls to put in them. Now the order of choosing the ball such that order of choosing the ball does not matters. Order of choosing the balls does not matters. Why it doesn't matters? Because ultimately if we choose the yellow ball and blue ball, first we choose the yellow ball, then the blue ball, ultimately we are left with yellow ball and blue ball. If we choose the green ball, the green ball and the blue ball, first we choose the green ball, then in the box we are having the green ball, and then we are choosing the blue ball, so we are having the blue ball. But ultimately in the box we are having 2 balls of 2 different colors, so whatever we are choosing, we are getting this only. So order of choosing does not matters. But what the balls we are choosing will matter. So for the first box we have 5 choose 2 options, and for the next box we have chosen 2 balls. We are left with 3 balls, and we need to put 3 balls in the box, so we have 3 choose 3 options. So total number of ways we can do this. First 5 choose 2. Now yellow ball here, red ball here, and the rest of the 3 balls here. So we can see whatever we are choosing here is creating a difference in here, and the net number of combinations formed are dependent on each other. So the cases are dependent. 5 minus 2 choose 3 equals to 5 choose 2 into 3 choose 3. So this is how we are choosing. We are grouping or distributing them. M balls we are having into groups of X, Y, Z. We can do this in M factorial by X factorial, Y factorial, Z factorial. How? Because M balls into groups of X, Y, Z. What we are having? First we will choose for the first box X. We are having M options. M choose X. Now we are left with M choose. Now M minus X balls are there because in the first box we have distributed x balls. So now we are left with m minus x balls and choosing y balls for the rest of them. And at last we are choosing m minus x. Here we were having how many balls? Here we were having m minus x balls and we chose y balls. So here we are having m minus x. If we consider it n, then here we are having n minus y balls. Now this n is m minus x. So m minus x minus y. Choose z equals
x plus y plus z.
m minus x minus y. M equals to m equals to
Distributing m things.
x plus y plus z. Because we are distributing m equals to x plus y plus z minus x minus y will give us z choose z. So this is m factorial over m minus x factorial. The basic formula of choosing NCR, x factorial into m minus x factorial over m minus x minus y factorial over y factorial. Multiplied by z factorial over yz factorial. M is what? X plus y plus z. X plus y plus z minus x minus y factorial. This is the value of m minus x minus y factorial. So this and this cancels, we are left with z. So it is z factorial simply. Simply z factorial over
Zero factorial equals to 1.
again z factorial because m minus x minus 0 factorial. Zero factorial z minus z factorial because this part minus z factorial, so it will be 0 factorial, 0 factorial and then z factorial. This is equals to z factorial. So this and this cancels. 0 factorial is equals to 1. M minus x also cancels out. We are left with m factorial, x factorial, y factorial, z factorial, which is the formula. Now, up to this, the arrangements of group does not matter. If we go back to this example, then there was an interesting thing. That the first box, whose capacity was 2, and the next box whose capacity was 3 could be arranged in 2 factorial ways, which is the arrangements. We can say that arrangements of group, because these are groups only. These boxes denote groups here. Boxes are equivalent to group, and they can be arranged among themselves in 2 factorial ways. So if the arrangement of group matters, then we will multiply it the number of groups, we will multiply it with the factorial of the number of groups formed. Here the number of groups is XYZ, that is 3 groups. And that is the important thing. In how many ways can we distribute 9 different fruits among 3 families such that each person in a family can get 1 fruit, and this should be there are. In how many ways can we distribute 9 different fruits among 3 families such that each person in a family gets 1 fruit? Each person in a family should get minimum 1 fruit. There are 2, 3 and 4 members respectively in the families. So we are having 3 families, say for example A, B and C, which is having 2 members. Suppose A is having 2 members, B is having 3 members, C is having 4 members. Our intention is to distribute the fruits. Our target is to distribute the fruits in groups of 2, 3 and 4. This is our target. So for the first family, family A, we are having 9 options and we will choose 2. For the next we are having 9 minus 2, we will choose 3, and here we are having 9 minus 2 minus 4 and 4. This will be 3. This will be 3, which is equals to 9 factorial over 2 factorial, 3 factorial, 4 factorial. Now we will not multiply it with 3 factorial. their arrangement is not 3 factorial because their arrangement is unique. Their arrangement is unique because it is given respectively. It cannot happen that family B is having 2 members because it is given respectively. It is already given that it is respective case. So 3 factorial is not possible. 3 factorial is not possible because it is given respectively, this word, which is the word of special focus, respectively. Now we just need to calculate. Five chocolates of different brands are to be distributed among 3 children such that the number of chocolate distributed are in an increasing order. In how many ways can we do this such that each child gets at least one chocolate? Five chocolates of different brand are to be distributed among 3 children such that the number of chocolate distributed are in an increasing order and each child gets at least one chocolate. So in how many, what are the possible cases or possible groups? Possible groups. The first is 1 chocolate, 2 chocolate. There are total of 5 chocolates, 3 chocolates. We have to start from the least, and the number of chocolate distributed are in an increasing order. But here we are getting that the minimum number of required chocolates, minimum number of required chocolates is 6 to satisfy the given condition. So number of ways is 0. Now the answer is not 0. Nine chocolates of different brands are to be distributed among 3 children such that the number of chocolates distributed are in an increasing order. In how many ways we can do this such that each child gets one chocolate? The question is same. Now the number of chocolate has increased since there was a shortage of chocolate in the previous question. 9 chocolates of different brands are to be distributed among 3 children such that the number of chocolates distributed are in an increasing order. In how many ways we can do this such that each child gets at least one chocolate? First, possible groups or possible distribution. What are the possible groups? The possible group is, we start with 1 chocolate, then 2 chocolate, 1 2, we have given 3 chocolate, 1 2 6, again 1 3 5, 1 4 4. This is not possible because the number of chocolates are in an increasing order. It's given. So now let the group start with 2 chocolate, 2 3 4. So these are the possible groups. These are the 3 possible groups, because if we go further, 2 3 5, this is not possible. If we start from 3 3 4 5, this is the minimum case for increasing order, which sums to 3 plus 4 7, 7 plus 5 12, which is not possible because the total number of chocolates given are 9. We are having 3 children, and these are the possible groups of distributing the children the chocolates. So for this case, how many ways we can do this? 9 choose 1, 8 choose 2, 6 choose 6. When multiplied, it's equals to 9 factorial over 2 factorial 6 factorial. Now this time, in the previous case we have seen that order of group was unique because it was given respectively, but now the order of group is not unique. If you are having 3 children, say A, B, C, the first children can get 1 chocolate, second children can get 2 chocolates, and the last one 6 chocolates. This is true. Now the first can get 2 chocolates also, B also can get 1 chocolate, C can get 6 chocolate, because it is not like that number of chocolates are to be in increasing order for this child ABC. This is also in increasing order if we just rearrange this ABC. So here the distribution of group matters, because the arrangements, because however we are distributing, the chocolates are in an increasing order only. 216 may not look, when in the case 216, this distribution may not look in increasing order, but we can just change this to BAC, then it will be 1 2 6. So now the chocolates are distributed in increasing order. So we are arranging them, we are arranging the children. We are arranging the children. Multiplied by 3 factorial. Multiplied by 3 factorial. Multiplied by 3 factorial. So we would just compute this 9 factorial, 1 factorial, 2 factorial, 6 factorial into 3 factorial. This is 9 factorial, 2 factorial, 3 factorial, 4 factorial into 3 factorial. Now we will just add them up. 3 factorial into 9 factorial over 2 factorial added with the second case 9 factorial over 1 factorial, 3 factorial, 5 factorial added with the last case 9 factorial over 2 factorial, 3 factorial, 4 factorial multiplied by 3 factorial multiplied by 3 factorial. So this will give us the total value. Now there is an important part. The same idea of m balls into groups of x, x, y That is, now two groups are similar, that is 8 chocolates among groups of 2 to 4. In how many ways can we do this? 8 chocolates among group of 2 to 4. Into or among 3 children's, among 3 children's. This will be 8 factorial over 2 factorial, 2 factorial, 4 factorial. Now the arrangement of this 2 to 4, how many arrangements does exist for this 2 to 4? This is permutation with repetition. 3 factorial over 2 factorial. So multiplied the arrangement of groups. So this is m balls into groups of x, x, y. Whenever there are cases of repetition. Let n be the number of ways of distributing 8 chocolates of different brands among 3 children, such that each child gets at least 1 chocolate and no 2 children gets the same number of chocolate. Find the sum of the digits of n. Let n be the number of ways of distributing 8 chocolates of different brand among 3 children, such that each child gets at least 1 chocolate and no 2 children get the same number of chocolate. This is again the case of increasing order. Just the question has been a little bit changed because the number cannot be same, so there has to be some increasing order only, or we can say decreasing also. This can happen in 1, 2, 5, 1, 3, 4. Let's try with 2. 2, 3, 5, 3. So 2 children are getting the same thing. This will happen in 8 factorial over 2 factorial, 5 factorial ways, and this will happen in, just you can calculate this, you will get the same thing. 8 choose 1, 8 minus 1 choose 3, 8 minus 1 minus 3 choose 4. You will get 8 factorial over 1 factorial, 3 factorial, 4 factorial. Now they can be arranged among the children in how many ways? 3 factorial ways. There is no case of repetition. This is also in 3 factorial ways. So we'll multiply it by 3 factorial. We will multiply this also by 3 factorial. Adding the two cases, we will get our answer. Entering to the next topic. Wait, before that, let's solve another one. Another problem. In how many ways we can distribute 12 students into rows of 2, 3, 4, 3? This is 2, suppose 3, 4, 3. They can be arranged in 4 factorial repeated items. What are the repeated items? 3 and 3. Write them in. 2 factorial. This is the number of arrangement of the rows. Now 12 students
4
can be
factorial.
distributed 12 factorial over 2 factorial, 3 factorial, 4 factorial. They can be grouped in 12 factorial by 2 factorial, 3 factorial, 4 factorial, 3 factorial. And then the rows can be arranged in, that is the group of person can be arranged in 4 factorial over 2 factorial ways. So this is distributing, or we can say grouping of repeated groups, we can say some groups are repeated. Practically we have to understand that whenever the arrangement will matter and whenever it will not matter, arrangement of group will matter. Where the question was into rows, into study groups, 12 students into study groups of 2, 3, 4, 3. Same question.
Solve it. There are 12 students.
Distribute 12 students into study groups of 2, 3, 4, 3. Distribute 12 students into study groups of 2, 3, 4, 3. Arrangement of study groups does not matter. That is not given in the question, but we have to conclude that. We can understand that arrangement of study groups does not matters. Study group of 2 is before study group of 3. What does that mean? That doesn't have a practical sense. So it is simply 12 factorial over 2 factorial, 3 factorial, 4 factorial, 3 factorial. Beggars method. In how many ways can we give $5 coins to 3 beggars? $5 coins to 3 beggars. First of all, important thing to note. In beggars method, we are distributing similar things. In beggars method, we are distributing similar things. $1 coins are similar In how many ways we can do this? We are having 3 beggars. Let them be x1 plus x2 plus x3, and we are having total 5 coins, that is rupees 5. Now in how many ways we can give them? Let us think for one way. 2 plus 1 plus 2 equals to 5. So this is what? 1 1 plus 1 plus 1 equals to 5. 1 1 is 2 only. 1 1 is also 2. So we can say that we are just choosing the one. If we imagine the plus symbol as 0, 1 1 0, 1 0 1 1, so their arrangement their arrangement will give us possible ordered pairs. Because 1 0 1 1 1 0 1, this is what? This is in the sense 1 3 1. This is again ordered pair. So in how many ways we are arranging them will give us the total number of different ordered pairs. That is the number of ways we can distribute them into the beggars. We have considered the plus symbol as zeros, the spaces as zeros, and they can be arranged in. There are a total of 7 things, 2 zeros and 5 1. Now this can be interpreted as the 7 things actually. These 2 spaces, these are spaces. 2 spaces create 3 occupancies. If we are having m spaces, it will create m plus 1 occupancies. What do I mean by occupancies? Like 3 spaces we are having, it will create 4 occupancies. This is occupancy. So m spaces will create m plus 1 occupancy. So 7 factorial can be just thought as. Now we are having 3 occupancies which are definitely created by 2 spaces. So 3 minus 1, and the number of things we are having 5 over 3 minus 1 factorial over 5 factorial. This can be written as what can I write? In terms of combination, we have seen that this 1 1 0 1 1 0 1, this will also give us 5 only. It can be thought of as selecting the position for 1 out of the positions that we are having, choosing position of 1 from the spaces. How many spaces we are having? Spaces we are having 5 plus 3 minus 1. So this is 5 plus 3 minus 1, choose 5. If we just expand this case for n things, earlier we were having 3 things, now we are having n things. This can be observed as this formula: x1 plus x2 plus x3 equals to r, where r was 5. We have seen the simple binary arrangement 1 1 0 1 1 0 1. This is one possible solution, one possible ordered pair. So we can select the position of 1 from the empty spaces. The total number of spaces is n plus r minus 1, and the number of 1 is equivalent to this. Which is the formula. Using this formula, we can find the number of non-negative integer solution of an equation. So this can be used to solve Diophantine equations. These are a kind of linear Diophantine equation. To find the total number of solution ordered pair of a Diophantine equation. How many ordered triplet x, y, z satisfies x plus y plus z equals to 12, where x, y, z are positive, including 0? In this formula also, the possibility for 0 has been considered. How? Because this binary arrangement, this can also be rearranged in 0 simply 0 1 1 1 0 1 1. This is empty, which indicates the ordered pair as 0 3 2, which also comes under this formula. We are covering all the aspects. So this formula is valid. x1, x2, xn can be 0 also. Just we will put the formula: 12 plus 3 minus 1, choose 12, which is equals to 14, choose 12, 14 factorial over 12 factorial 2 factorial, 14 into 13, 7 into 13, which is the answer. Let's move forward. How many ordered triplets x, y, z satisfies x plus y plus z equals to 12 such that x greater than 2? X is greater than 2. So the minimum value of x, they are integers. is 3, y comma z minimum is 1. So can we consider x as 3 plus p, y as, where p is non-negative integer, that it can be 0, that's why non-negative integer. All positive plus 0 means non-negative. Y can be considered as 1 plus q and z can be considered as 1 plus r. So the minimum values will be also satisfied. Now what we are left to find? We need to find this 3 plus p. P can be 0 also. So the minimum value of x is also satisfied, that is x is greater than 2. It's not greater than equals to. It's strictly greater than 2. 3 plus 2, this is x plus 1 plus q plus 1 plus r equals to 12, or p plus q plus r plus 5 equals to 12. This is simply 7. So the number of ordered pairs are, there we are having 3 things, 7 plus 3 minus 1, choose 7, choose 7, that is 7 plus 3 minus 1, 9 factorial over 7 factorial, 9 minus 2 factorial, 9 minus 7 factorial, 2 factorial. This is 9 into 8 by 2. Nine 4 ja. Answer is 9 into 4. This part you just see. 9 into 4, which is equals to 36. This is the number of answer. Are you getting the system? This is the most important part. This is the most important part. This consideration, and this is what? Simple beggars method. Simple beggars method. We have seen beggars method for negative terms. We have only for positive term, but this is negative. How we will do this? Y comma z greater than 1. X plus y plus z equals to 13. Nice question. At least 2 pages we need. Try it. You can try it. You can solve it. Let's solve it. How many ordered triplet satisfies x plus y plus z equals to 13 such that x, y, z are integers satisfying x greater than minus 3? What are the possible values of x in negative terms? Let's think. Because whenever it's a case of positive, we can do this by simple beggars method. We can think of y as some a plus 1 and z as some b plus 1, where a and b are non-negative integers. A comma b greater than equals to 0. A comma b belongs to integer. Set of integer is denoted by the symbol z. This is the first consideration, and let's sort out the case for negative 1. That is when x equals to minus 2. We'll do like this: minus 2 plus a plus 1, that is y, and b plus 1, that is z, equals to 13, or a plus b, these and these are cancelled, equals to 13. How many solution it is having? (13) plus 2 minus 1, choose 13, equals to 14, choose 13. The answer is 14. When x equals to minus 2. Now let's come for the next case. When x equals to minus 1. A plus b equals to 12. How many ordered pair would satisfy this? 13. So we have completed the cases of negative terms. Now the next case is what? X equals to 0. Why we would consider? Because whenever we are using the formula, we are considering for 0 to positive integers, from 0 to all the positive integers. So that is the technique that we will just simply manually find out the ordered pair by considering the negative values. That can be one approach. There are a lot of different approaches. Are there. So 13 and 14. Now simply x plus a plus 1 plus b plus 1, because now x ranges from 0 to 13, equals to 13. Not 0 to 13, we are restricted to 11. X plus a plus b equals to 11. The solution pairs are 6 into 13. What is the value? This is 65 plus 13, 78. Okay. This is 75, not 75, 78. So the total number of ordered pairs are 78 plus 13 plus 14. You add them up, you will get the answer. Just the important idea is this. This is the important idea that we need to focus. How many ordered pair of positive integers satisfy x, y, z equals to 20? This kind of question appeared in PRMO. Among the recent PRMO, this kind of question appeared. Simple thing. X, y, z equals to 20 can be written as 2 square into 5. Now this x, y, z can be written as x can be considered as sum 2 to the power a1, 5 to the power b1. Y can be considered as same 2 to the power a2, 5 to the power b2. Z can be considered as 2 to the power a3, 5 to the power b3. Now we'll start with this case, that is 2 to the power a1 into 2 to the power a2 into 2 to the power a3 equals to 2 square, or a1 plus a2 plus a3 equals to 2. The number of ordered pairs satisfying this are 3 plus 2 minus 1, choose 2. 4, choose 2. 4 factorial by 2 factorial, 2 factorial. That is 4, that is 6. That is 6. I need another page. So 6 cases we are getting. Now for 5. For 5, how many cases will we get? That is b1 plus b2 plus b3, 5 to the power is to 5 to the power 1. b1 plus b2 plus b3 equals to 1. How many ordered pairs satisfy this? 3, choose 1. 3 ordered pair. So the answer is, now we will just multiply them. For this b1, b2, b3 we have got 3 pairs, 3 ordered triplets multiplied by the 6 ordered triplets that we got earlier. Our answer will be 18. This is the important thing. We have to understand that the cases are dependent. And this is the important thing. How many ordered pairs of integers satisfies x, y, z, w? Equals to 36. X, y, z, w equals to 36. Let's find out. 36 can be written as 2 square into 3 square. So similarly, the earlier approach we will use, that is x equals to 2 to the power a 1, 3 to the power b1, y equals to 2 to the power a2, x equals to 2 to the power a1, 3 to the power b1, y equals to 2 to the power a2, 3 to the power b2, z equals to 2 to the power a3, 3 to the power b3, and w equals to 2 to the power a4, 3 to the power b4. These are the consideration that we need to do first. Now a1 plus a2 plus a3 plus a4. a1 plus a2 plus a3 plus a4 equals to 2. b1 plus b2 plus b3 plus b4 also equals to 2. How many ordered pair will satisfy this? This is very simple. 4 plus 1, choose 2. That is 5, choose 2. 5 choose 2, which is equals to 5 factorial over 2 factorial over 3 factorial. 3 factorial is 6, 2 factorial is 2, 2 6 are 12, this is 10. There is also same thing, 4 plus 1 choose 2 equals to 10. So we are getting 10 into 10, 100, 10 into 10, 100 ordered quadruples. Now the important thing of the question is that how many ordered pair of integers? It's not positive integer. It's not positive integer. It can be negative also. So among x, y, z, x, y, z, w, if one of them is negative, this one is positive, this one is negative, this one is positive. This is one case. We can arrange the negative and positive things in 4 factorial over 2 factorial, 2 factorial, which is equals to 6 ways, and all of them can be negative. That is another case. X, y, z, w, all of them are negative. This is also a possible case. There is only one option. This was for the positive cases. This is for positive integers. Now we are having 3 cases, all positive. That is having 100 integers. 2 are positive. 4 oblique, all negative. All negative. 2 positive, we are having 6 into this number 100, and all negative we are having 1 into 100. Adding them we will get 100, 200, 600, 800 pairs. So this is tremendous. It doesn't seems like we can get so many different numbers of pairs, but it's happening. It's happening. Using the same idea, we will approach this 20 whole to the power 21. Pairs of integers. I'm just giving the hint that x, y, z all positive and negative, negative, positive, which can happen in 3 factorial over 2 factorial ways. We can arrange them. That is 3 ways. 2 negative, 1 positive. This can happen in 3 ways. That is the hint. Last question that we'll solve. Find the number of ordered triples of positive integer. They didn't give negative integer. So this is very easy for us. ABC equals to 108. Prime factorizing 108. 2 into 54. 2 into 3 into 54. Just a minute. 108. 2. 54. 3. 1. 18. 3. And we are having 6, 3, 2. This is the prime factorization. So 108 equals to 2, 3, 3, 2. ABC equals to 2 square into 3 cube. Consider the same thing. Sum A1 plus A2 plus A3 equals to 2 in equals to x. Which is so the 60. This 108 is quite easy because we have solved it for negative. Have seen for some with the use of binomial theorem, the idea of beggars theorem can be extended. In future we will see. Beggars theorem, the important thing is that whatever thing we are distributing needs to be identical. That is the important thing in Beggars theorem. And another important thing is that we will see Beggars theorem with binomial theorem. Beggars theorem with binomial theorem. This is not Beggars theorem, this is Beggars method. Beggars method. Beggars method. Binomial theorem and Beggars method. Then how we can generate functions using binomial theorem to solve Beggars method's problem.